A DC distribution board, or DCDB, functions as an internal firewall for electrical grid facilities. It contains high-energy faults to a single panel, preventing localized surges from triggering cascading failures across the wider substation network. Validating this hardware requires field engineers to reconcile competing manufacturing and safety thresholds from organizations like the IEC, IEEE, and NEMA. To resolve these conflicts, engineers apply the stringency governance principle. If a project specification, manufacturer manual, and international standard differ, the technician defaults to the most rigorous approved requirement. The highest threshold takes precedence. Enforcing a strict hierarchy of standards ensures individual component limits meet the maximum possible safety ratings. This discipline prevents a localized fault from breaching the insulation and damaging surrounding grid infrastructure. The commissioning protocol operates through a threefold validation matrix. We test the panel's physical integrity, its internal control logic, and its dynamic response to simulated faults. Before the panel is opened, technicians implement a strict lockout-tagout, or LOTO, procedure. This physically prevents anyone from energizing the board during the testing phase. Testing zones require rigid environmental boundaries. The area is isolated with warning tape, proper grounding connections are verified, and all personnel must wear ARC-rated personal protective equipment. No test leads touch a terminal until calibration certificates for all primary test equipment are verified. The instruments measuring these exact tolerances must provide absolute accuracy. Strict procedural discipline and precise instrument calibration ensure the engineer remains physically separated from live DC circuits while the board is under test. The testing sequence begins by proving the physical isolation and insulation integrity of the DCDB's internal bus bars, the solid copper pathways that carry the main current. The panel is mechanically isolated from all external power sources. This includes disconnecting battery chargers, isolating the main battery banks, and removing any capacitive backfeeds that hold residual charge. Next, engineers perform a visual inspection. They verify proper busbar clearances, check the integrity of cable glanding, and confirm that torque marks are present on every tightened terminal. This schematic shows the insulation resistance test setup. A targeted DC voltage is applied from the phase R terminal directly to earth ground. Engineers verify high resistance, confirming intact insulation, then record phase Y and phase B to ground vectors. Because insulation resistance testing applies high voltage, the busbars act like capacitors and store electrical energy. Engineers must actively discharge every busbar to earth immediately after the test concludes to prevent shock. Confirming this baseline physical isolation ensures the copper paths are secure. Without this step, injecting voltage to test the control logic later could short out adjacent components and cause severe damage. Copper pathways only function if the panel knows when to open or close them. Supervision relays provide this logic and must trigger exactly on command. This diagram illustrates a secondary injection test. A variable DC voltage source connects directly to the relay's internal coil at terminals 13 and 14. The technician increases the voltage to pinpoint the pickup threshold required to physically close the contact. The recorded pickup voltage must align with the manufacturer's established limits. For many supervision relays, this mechanical action must occur at exactly 80% of the coil's rated voltage.
The technician then reverses the procedure, slowly decreasing the injected voltage. They record the dropout point, capturing the exact voltage level where the contact releases and opens the circuit. By comparing the pickup and dropout voltages, engineers calculate the relay's reset ratio. They also measure the internal coil resistance to ensure it matches the original factory datasheet, proving the windings haven't degraded. Establishing these precise voltage thresholds prevents the relay from nuisance tripping during minor power fluctuations, while guaranteeing a hard-coded response when genuine voltage fags occur. The next layer of testing verifies the dynamic fault protection. Miniature circuit breakers, or MCBs, isolate localized overcurrent events before they spread to the main busbar. This procedure begins with a mechanical continuity check. With the breaker locked in the closed position, a multimeter is connected across the poles to prove an uninterrupted electrical path exists through the device. Once continuity is confirmed, the tester configures a secondary current injection kit. This machine simulates a fault by pushing precise levels of current through the MCB, scaled to its specific amp rating. This chart displays logarithmic time current curves.
The validation requirement is measuring the exact millisecond the breaker trips and plotting that time against the injected current. The coordinates must fall within the shaded orange tolerance band, otherwise the breaker is defective. Verifying that precise fraction of a second ensures the MCB physically opens the circuit fast enough to stop an overcurrent from damaging the upstream wiring. Molded case circuit breakers, or MCCBs, require significantly higher testing parameters. These devices handle larger electrical loads coming directly off the main distribution feeds. To test them, engineers shift to primary current injection testing. This setup uses a heavy-duty unit like the Odin test kit shown here to push massive amounts of actual current directly through the breaker's physical poles. The protocol dictates injecting a simulated fault, driving between 250 and 300% of the breaker's maximum rated current straight into the system. Because the thermal and magnetic forces at these loads are extreme, technicians must record the time and current from the display simultaneously. At 300% load, the margin for mechanical error is minimal. Recording an accurate trip under a 300% load without any structural failure validates the MCCB's capacity to arrest a catastrophic short circuit. Subjecting hardware to extreme tolerances occasionally reveals defects. Engineers document any delayed trips, absolute failures to trip, or localized abnormal heating across the terminals. If a supervision relay exhibits contact chatter or sticks during the voltage drop test, it points directly to hidden coil degradation or mechanical misalignment within the casing. The DC panel relies on external inputs. This requires engineers to cross-check results with current transformer and voltage transformer testing packages located elsewhere in the substation. If any of those external dependencies are incomplete, project protocol requires them to be formally isolated and tracked as controlled, registered punch list items. An anomalous test result identifies a latent physical vulnerability in the hardware. These findings necessitate immediate component isolation and replacement to prevent a potential field failure once the board is energized. The culmination of the testing protocol is the hold point. This is a procedural barrier, mandating that no single technician has the authority to release the panel for active service without witness verification. An independent operations witness executes a mandatory physical walkdown. They verify physical barriers are restored, temporary test links are removed, and every bus bar completely discharged. The lead engineer then compiles the evidence package. Every calibration certificate, signed test sheet, and specific standards reference is bound into a single traceable document, proving compliance. This final evidence package transforms thousands of technical readings into a documented record of operational readiness. By signing off on these results, the commissioning team establishes the final layer of professional accountability required to energize the board.